Hello there. In this video, we're going to introduce another application of exponential logarithms and also rational functions, and that is in regards to the what is called logistic function, which is often used in population modeling. So the logistic function is given by the form f of x is equal to k divided by 1 plus e to the power minus r times x minus x sub c. We're going to talk about each of these components, what k, r, and xc means, and also how to interpret this function overall and use it. Alright, so in general, every time you have, say, a general model and you want to sort of understand it, usually the best way to start off is by assigning particular values for these particular parameters k, r, and xc, to sort of get a general basic feeling for what is going on. So I'm going to do precisely that. So I'm going to consider a simplified version of this logistic function, in particular 1 over 1 plus e to the minus x, right? So in regards to the more general form, we're letting k be equal to 1, we're letting r be equal to 1, and we're letting xc be equal to 0. And sometimes we refer to this simplified version as the standard logistic function, right? And if you're familiar with some basic probability and statistics, then maybe you are familiar with the normal and the standard normal distribution. So it's sort of like a parallel between those two concepts, right? So just some basics with this particular function. For example, if we evaluate this at f of 0, we're going to get 1 divided by 1 plus e to the minus 0, which is going to be 1 half. We can also see a couple things. As x tends to positive infinity, we know that e to the minus x is going to tend to 0 because that is an exponential decay term. So that means this function f of x is going to get close to 1 over 1 plus 1, 1 over 1 plus 0, sorry, and that's going to be equal to 1. And as x gets close to minus infinity, we know that e to the minus x is going to get really big on the left-hand side of that graph, right? So that means this function f of x is going to get close to 1 over an arbitrarily large number, which, as we know for rational functions, is going to get close to 0. So combining these three concepts together, we can generate a sketch for this standard logistic function, right? So we have the x-axis, the y-axis, right? So when x is equal to 0, we have 1 half. We have a horizontal asymptote at y is equal to 1. We have a horizontal asymptote at y is equal to 0. And then once we sketch this curve, we should have something that looks like this, right? And some people refer to this shape as a sigmoid curve. It's almost like a shape that looks like an S on its side. So this function isn't an even function. It's not symmetrical at the origin, therefore it's not odd. But it definitely does have some sort of symmetry associated to it. So let's see if we can derive a property for the symmetry of this particular standard logistic function. And then we'll get back to the general logistic function in just a moment. So as we already know, the standard logistic function is going to be 1 over 1 plus e to the minus x. So if we plug in negative x, then we're going to get 1 over 1 plus e to the power of x, right? So one thing we can do is we can multiply top and bottom of these equations, say by e to the x and e to the minus x respectively. So once we do that, we're going to get equivalent forms. So f of x is going to be equal to e to the x over 1 plus e to the x. And f of minus x is going to be the same thing as e to the minus x over 1 plus e to the minus x. And I've just rearranged the denominator by putting the 1 on the left instead of the right-hand side, which is the direct result you get when you distribute those exponential terms. Right? So here are these two things, and definitely there is some relationship. So what I'm going to do is add these two because maybe we can cancel some things. All right, so what is f of x plus f of negative x? And remember, exponential functions are never negative, so these terms, e to the x and e to the minus x, are never going to be equal to negative 1. So the domain for f and f negative are going to be all real numbers, right? So just keep that in the back of your mind, just for the time being. So what is this going to be? So this is going to be e to the x over 1 plus e to the x, and then plus e to the minus x over 1 plus e to the minus x. And then we can get a common denominator by multiplying the left by the right and the right by the left denominator. So that's going to give me e to the x times 1 plus e to the minus x plus e to the minus x times 1 plus e to the x, all over the product 1 plus e to the x times 1 plus e to the minus x. Then I'm going to distribute everything, so I'm going to have e to the x plus 1 plus e to the minus x plus 1 all over. All right, so what do we get here? So distribute this, so we're going to get 1 plus e to the minus x plus e to the x plus 1, right? So on the numerator, we get what? So we get 2 plus e to the x plus e to the minus x. On the bottom, we also get 2 plus e to the x plus e to the minus x. And since the top and bottom are the same for all values x, this is always equal to 1. So therefore, we have the following result, that f of x plus f of negative x is going to be equal to 1 for all x in the set of real numbers, right? So that's pretty much like the even-odd sigmoid symmetry that the logistic function has, right? So now let us go into the general applications for the logistic function, in particular the original standard, non-standard logistic form. All right, so as I mentioned before, one of the applications that the logistic function has is modeling population growth. So population growth, right? So I'm going to just denote a couple things. I'm going to let P0 represent the initial population. And when I say initial, I mean at time t is equal to 0, so some point of reference in time. And I'm going to let R represent the growth rate per unit time, right? And keep in mind this per unit time and this time here should be in the same units. All right, so how can this logistic model be used here? And it's based on the following scenario. So eventually population grows to a rate for which competition occurs, for which the rate of growth diminishes towards equilibrium. So what exactly does that mean? So if we sort of think about a standard population region, and let's assume that the maximum amount of values that can exist in this particular set is k. So k is going to correspond to the max population, right? So as you begin to populate this, so 1 turns into 2, that turns into 2 exponentially, and eventually this populates extremely quickly at an exponential rate, right? But once you start to fill this set up and we get closer and closer to this value of k in terms of the population size, the number of resources tends to diminish extremely quickly as well, right? So resources, living space, and so on get smaller, right? So that's where the competition sort of comes into play, right? So the rate is going to slow down until everything sort of goes to equilibrium, pretty much a steady state solution, right? So that's pretty much where this shape sort of comes into play. So it has sort of like an exponential shape, and then stuff starts to slow down at some point in time, and then it grows, but not as fast as it used to, right? Due to competition, right? So instead of reproducing like 3 kids or 4 kids, that's going to bring us down to 2 or 1 to reduce competition and to make things pretty much easier, right? And that, of course, approaches this top asymptote of y is equal to k, right? Okay, cool. So once we take all these things into consideration, and if you study differential equations later, you can sort of derive this particular function. But the function model is going to be p of t is going to be equal to k, all divided by 1 plus k minus p0 all over p0 times e to the minus rt, right? So again, k is going to be the maximum population, p0 the initial amount at t is equal to 0, and r the initial growth rate. So I leave it as an exercise to show that p of 0 is actually just equal to p0 in this general model. So let's look at a particular example of how we can use this. So let us assume, let t be in years, and let's assume that the initial population is 100,000. So let the population be in hundreds of thousands, I guess. So we're just going to, actually just thousands. And let r be equal to a 2.3 percentage rate. And let k be equal to 500k. So at some point of reference, we're going to be at 20% of the capacity for which we can store, right? So let's generate our model for the population at any year time t. So that's going to be equal to 500 all over 1 plus 500 minus 100 over 100, so 100, times e to the minus 0.023 times t. So 500 minus 100 is 400, and 400 over 100 is going to be 4. So we can look at a more simpler looking model. P of t is equal to 500 all over 1 plus 4 times e to the minus 0.023 t, right? And I'll leave as an exercise to figure out. If you remember, the original logistic growth model was in the form of minus r times x minus xc, where xc was the center of the distribution. What is the value of xc in this particular equation? Right? So once you actually go through that process and you figure out what xc is and so on, so we're going to have our 2 asymptotes. We have our sigmoid curve, right? And one can find, let's assume that this is the y-axis, and let this be 20%. So that's pretty much why it's not symmetric as it was before. So let this be 100 and let this be 500, right? So this is going to still increase at an exponential rate, right? So the middle of the distribution, so this is going to be xc, that's going to where sort of the steepest incline is going to be. So after this value is going to sort of go off or taper off into equilibrium mode, right? So after 50 years, if we keep this constant growth rate, what will be our population? So I'm going to plug 50 into our function. So that's going to be equal to 500 all divided by 1 plus 4 to the e minus 0.023 times 50. And you can find that that's approximately equal to 220.6. So it's still just slightly above where we were before, right? So we haven't reached the halfway point, the 250 point, and it's been 50 years, right? So if your model sort of predicts that, maybe you want to encourage a higher growth rate, right? And there's many mitigating factors to sort of catalyze that particular action, but I'm not going to go into the whole entire social engineering and economics that would go behind that discussion. So sometimes in these scenarios, we would like to figure out, well, how long would it take under this model for the population to reach a certain amount, right? So we're sort of solving an inverse problem in this particular approach. So if we sort of look at the general form of this, we can usually rewrite this in a more simpler fashion, more in particular k over 1 plus alpha times e to the minus rt. And here I'm just letting alpha represent the k minus p0 over p0 term in the original expression that I expressed for the population growth model. So let's solve this equation for t. So that should not be hard. So let's solve for t. Right? So I'm going to begin by multiplying both sides by 1 plus alpha e to the minus rt, and that's going to give us k over pt. So I'm going to multiply both sides by the denominator and then divide both sides by pt. So we're going to assume that pt is not 0 here. And that's going to be equal to 1 plus alpha e to the minus rt. And I'm going to subtract 1 and then divide by alpha. So once I do that, I'm going to have e to the minus rt is going to be equal to 1 over alpha times k over p of t minus 1. Then I'm going to take the natural logarithm of both sides of this expression. So I'm going to have minus rt is equal to the natural logarithm of 1 over alpha times k over pt minus 1. We have a product of two functions on the interior of the logarithm, so you can split that up into a sum, but I'm not going to do that here because our expression will be even more nastier than what it will be. Well, that's subjective, I guess. And then I'm going to have that t is going to be equal to minus 1 over r times the natural logarithm of 1 over alpha times k over pt minus 1. Right? So that's the general representation for t in our logistic growth model. So now we can directly answer the following questions. So question, so when will the population be equal to 450,000? Right? So plugging in everything we have, so t is going to be equal to minus 1 over the growth rate, so 0.023 times the natural logarithm of 1 over alpha, so that's going to be equal to 100 over 500 minus 100. So 100 was P0, 500 is K. And then that's going to be multiplied by 500 over PT. So that's the value at the time for which we're searching for. So that's going to be 450 minus 1. Right? So clearly that's going to be a positive number. This is going to be a negative number because 500 over... No, it's going to be a positive number. Yeah. So that's going to be a positive number as well. But my claim is that this number is going to be between 0 and 1. And how can I be so sure about that? Well, if this is to work out, notice we have a negative sign on the outside, right? So the only way that this time is going to be positive, in particular greater than 0, is if this number on the end here is in between 0 and 1. And I leave for you to verify that that is the case. So once you actually work this out, you're going to have that t is going to be equal to 155.8 years. Right? So if you're okay with all of these things, this particular growth rate, this maximum population, because sometimes you can increase that maximum population depending on what you're trying to do with this particular model. So in 155.8 years, if this logistic model is actually relatively accurate, then you expect your population to be 450, which is 50 off the maximum capacity. So this is just another application of exponential, rational, and logarithmic functions. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.